operation classroom. Uh, we are now discussing GATE 2023 question number 13. So here we have two complex numbers given by these 2 plus 3i and negative 2 plus 3i, and this is the function. We have to find out whether this function is less than 0, 1, greater than 1, or equal to 1. We know for any complex number a plus ib, let's say, the absolute value or the magnitude is given by this, and the argument is of course given by this. This absolute value is of course the distance from the origin, and this is of course the angle from the positive real axis. So if this is my real axis and this is my imaginary axis, so we have to measure the angle from the positive real axis. So Z1, 2 plus 3i. So this is the absolute value square root of 13, which is 3.61. And the argument, of course, is tan inverse 3 over 2, 56.3 degrees. And this is in terms of 0.98 radian. Same thing with Z2. So we do that. The absolute value, of course, will remain the same. And the argument, of course, here, since this is in the negative direction, 3 by 2, so we have to add pi because this is in the second quadrant here. So this is the second quadrant. And this should be 123.7, which is 2.16 radian. So if we diagrammatically show here, as we have seen, so this is my real axis. Let's say this is my imaginary axis. So from the origin, so this is my 2 plus 3i, the complex number. This is 2 and this is 3. And this value is, of course, distance from the origin. So this is square root of 13, which is 3.61. And this is the angle 56.3 degrees. Same thing with Z2. So this is negative 2 plus 3i. So this is negative 2 plus 3i. That's the second complex number. And the absolute value, of course, remains the same here, 3.61. And the argument, of course, as we have seen, is 123.7 degrees. So this angle is 123.7 degrees. So if we add these two complex numbers, so this would be 6i. Of course, there is no real part, only imaginary part. So it has to lie on the positive imaginary axis. So it has to lie right here. So this is my 6i. So this is my 0. So this is right here. And this angle, of course, has to be 90 degrees. So this is my Z1 plus Z2. Okay. So we have to find out where the value of this or the range of value for this function. So if this one is the absolute value of Z1 and this is the absolute value of Z2, and by parallelogram method, we can just do that. And if we take the triangle inequality, we know this value will be always less than this plus this from the triangle inequality. So this one, of course, is this one right here. And this one, of course, is this one right here. And this one, of course, is this one right here. So this is going to be always less than this plus this. So numerator is always going to be less than the denominator. So so f has to be less than 1. So this is the correct option. In fact, we can check the value also. So as we said, B is the correct option, and F value is of course 6 over F value is, this is the 6 value. So this is the value of 6 over this square root of 13 plus square root of 13. So 2 over 13. So this is less than 1. So this is a very simple answer. I just want to show the chemical engineering application of this one. We know for a complex number, a plus ib, this can also be expressed in terms of the polar form as this one. And the associated sinusoidal forms can be expressed as a cosine function or as a sine function. These are standard trigonometrical identities, so these are very easy. So if I apply this one, let's say for Z1, so 2 plus 3i, if Z is expressed in the sinusoidal, let's say temperature input to a particular heat exchanger or to a vessel. So this could be expressed as 3.61, which Z1 we have seen. This value is magnitude 3.61. And remember, this is 0.98 radian. Rad. So the associated function should be 3.61 cos of omega t plus 0.98 radian. Similarly, for Z2, this would be 3.61 cos omega t plus 2.16. We have seen this one for Z2, this 3.61 and this 2.16 radian. Now, let us see what could be an application. Let us say we have a CSTR, we have a CSTR, and there is a, let's say, flow variation or concentration variation or temperature variation. And let's say these are in terms of like a sinusoidal variation, oscillating flow or oscillating temperature or oscillating concentration. Then what really happens? So assume, let's say this is a first order CSTR. So this is my Z1, as we have seen, and this is my Z2. These are oscillating flows or concentration coming in, or it might be the temperature. And this was Z1 plus Z2 is 6i. So assume the first order CSTR. If we assume first order here, let's assume omega is equal to 1 and tau is equal to 2. So this would be this one right here. So the outlet phasor would be Z in, which is this one right here. And G of this for the CSTR is this one we have seen. So we do a little bit of math and that's what we get. So Z out would be, Z out would be 2.68. See, this has been attenuated. So this was 3.61, 3.61. This has been attenuated. So that's basically what happens when there is a, well, there are two sinusoidal flows coming in, and because of the resonance time in the CST or holding capacity, there's an attenuation, and the phi out also can be calculated, which is 0.464. So let us show this one diagrammatically. So this is my Z1. So this is my Z1 right here. As you can see, this is my Z1 is an oscillating sinusoidal flow. So this is my arm. And of course, as you can see, this is 3.61. And there is a phase lag of 0.98 radians. Similarly, for Z2, which is this one right here, as you can see, this is my Z2, another flow or temperature variation, which is going to the CSTR, which is this. And we have just calculated the Z out will be 2.4. So this dotted line, that is a Z out, as you can see. So this has been attenuated. So as you can see, this was around 3.61. This has been attenuated. And there's, of course, a lag of 0.46 radian. So this is really called the dynamic smoothing of oscillation or attenuation of oscillation. And the delays of response is due to the tau or the holding time of the CSTR. So hopefully this gives you an idea about how this complex numbers can be utilized for our control applications in chemical engineering.